Today, we're going to learn how adding nodes modifies the underlying data structure in a map. Hello, I'm James Helfrich. C++ implements the map using a binary search tree, but not just any binary search tree, a red-black balanced binary search tree. To see how this works, let's see how adding nodes to an initially empty map will modify the underlying data structure. We'll start with an initially empty map of grades, where a grade has an integer corresponding to the course number and a float corresponding to the student's grade. As a reminder, let's take a look at those red-black rules. Case 1, when I have no parent, an initially red node becomes black. Case 2, where the parent is black, then I don't have to change anything. Case 3, where the parent and the ant are red, and then we turn the parent and ant black, but the grandparent turns red. And case 4 involves the parent being red and the ant is black or does not exist. In this case, we have to do some sort of rotation, and there are 4 subcases there. So initially, I'm going to add 0.94 to the key 165, because that was my grade, 94% in CS 165. Now, all nodes are initially red, and so this is going to activate case 1 because the root has to be black. Now we're going to try to add the key value pair of 124 and 97%. Now, we always add a node as red. Since 124 is to the left of 165, then I just add, this is case 2, and I add my red node. Now I want to add the key value pair of 235 to 89%. Now, 235 is greater than 165, so I'm going to add the 235 node to the right of it. And initially, it's red, and this, once again, is going to activate case 2. Now I'm going to add 213. Now, 213 is greater than 165, so it goes to the right, and is less than 235, so it goes to the left. And now I'm going to add another red node. But now I have 2 red nodes in a row, and that does not work for red-black tree. So this is going to activate case number 3, where the parent and the ant are both red, the parent being 235 and the ant being 124, and they're going to become black. Now, when I change that, that means the grandparents become red, and that goes back to rule number 1, where I have to turn the parent black. In my final case here, I'm going to add the key value pair of 246 to 85%. 246 is greater than 165, so it goes to the right. It's greater than 235, so it goes to the right. And now I'm going to add a red node there, and this is just case 2, where my parent is black. Now my red-black tree is finished. Let's do the problem again, except with a slightly different order. I'm going to have the same integer float key value pair. So initially, 124 is 97, and since I add nodes as red, and I'm going to activate case 1, and the root node becomes black. Now, 165 initially goes red. Since 165 is to the right of 124, I add a red node to the right of it, and this activates case number 2, and I'm going to add the node. Now, 213 is greater than 124 and greater than 165, so it goes to the bottom right of 165. I'm going to add a red node, but I can't have 2 red nodes in a row. Now, this is going to activate case number B, where the parent is red and the grandparent is black, and I'm going to perform a rotation. Next, I'm going to add the key value pair of 235 and 89%. 235 is greater than 165, so it goes to the right. It's greater than 213, so it goes to the right. So now I'm going to add it to the right of 213. Once again, I'm going to have 2 red nodes in a row, and that's not going to work. So I'm going to have to activate case 3, where my parent, 213, and my ant, 124, are both red, and I'm going to swap them to black. My final node I'm going to add is 246. 246 is greater than 165, greater than 213, and greater than 235, so it goes to the right and bottom of 235. Now, once again, I have 3 red nodes in a row. So what am I going to do here? It's not going to be case 1 because I'm not the root. It's not going to be case 2 because my parent is not black. It's not going to be case 3 because my parent and my ant are both not red. I don't have an ant. So it must be case 4, where my parent is red and my ant does not exist. And this, once again, is going to be 4B, and I'm going to have to perform a rotation. And that concludes this. This is example 16.2 and 16.3. Borrowing heavily from the binary search tree red-black algorithm. All this is in a C++ data structures textbook.